So our first speaker was a statistician. The second speaker, Robert Jack, would be a physicist. So he's going to be speaking about how breaking detailed balance can accelerate convergence to equilibrium.
Great. So thanks very much to the organisers for organising this nice meeting. I wasn't quite sure who would be in the audience and what I should say. Can we just do a quick poll? So who calls himself a statistical physicist? Okay, and who calls himself a Bayesian statistician? Okay, and that's pretty much everybody. Okay, great. Okay, I'll try and... there's not much physics in here. I'm kind of assuming that there wouldn't be so many physicists, and the physicists would know a lot of it anyway. So it's more aimed at the stats guys, but maybe that's too hopeful. So if things are not clear, just interrupt me, tell me that you don't understand. I don't mind if I don't get to the end. So I'm from physics in Bath. This is joint work with Johannes Zimmer and Marcus Kaiser, who are both in maths at Bath. So Marcus is our PhD student who was supposed to be here, but unfortunately can't make it. And Johannes is really an analyst, so he really does like PDEs and existence and uniqueness and all these things that I don't understand. And you can find out about this work that I'm going to talk about mostly in this paper, which is now out in JSTAT. So a quick outline of what I'm going to say. So some motivation. So what in physics we call detailed balance is what in stats people call reversibility of Markov chains or Markov processes. And the question is whether we should design our MCMC samplers so that reversibility is broken in order to be more efficient. That's the idea. Is that true? It seems to be true, and the question is sort of why. I'm going to talk about this large deviation method for analyzing how fast these Markov processes converge to equilibrium. So as far as I can understand it, this idea came from Rabelais and Spiliopoulos about a bit less than 5 years ago. Certainly their papers are the place to look it up. It's not at all original to us. But I'll talk about something that we did with it to do with looking at particles on the hydrodynamic scale. I'll say what that is. And then we have a sort of geometrical idea for why it might be useful to break detailed balance. And that's the main thing that I want to kind of present to you. It's a bit of a sort of loose, hand-wavy picture, but it has some mathematics behind it, which you can mostly find in the paper. So what do we do in statistical physics all day? So this is just a picture from one of our papers with my colleague Nigel Wilding in Bath and our postdoc Doug Ashton. So what's going on here? So this is just two pictures of the same system. So there's two kinds of particles here. There's some small spheres which are blue, and there are some larger indented spheres which are orange. An indented sphere is just a sphere where you chop out another sphere. So it's like a sphere with a dimple in it. And what happens is that these orange particles, they go and sit one in the dimple of the other, so they make these kinds of long chains that line up. And it's a model for a particular experimental system which can be made, in which the typical size of these orange guys is about 1 micron. So, yeah, 1 micron. And the little blue guys are about 10 times smaller, maybe. So this is something that can be done in experiments, but this is obviously a simulation. So how do we describe this kind of system? So each particle, I, so there are n particles. Each particle with I from 1 to n has a position, which is in some domain lambda, which is in R3. So that's what we call the simulation box, would be lambda. And then each particle would have a position, and also each of the orange particles would also have an orientation, which I didn't put on the slide, but just imagine somewhere there are some orientations as well. So that's the state of the system. And then there's a distribution over these configurations which has this shape. So pi is somehow the distribution. So d pi of r is somehow some sort of prior, which in our case is just completely flat, completely uniform, times some density function, which has an exponential form with an energy E and a temperature T. So T would be 1 over beta from before, E would be E, R would be either X or theta or some other letter I've forgotten already. But hopefully it's clear that we're all on the same page trying to sample from this distribution, right? And in physics we often say the aim is just to generate some representative samples from pi. Usually you generally want to represent these samples in order to compute expectation values. That would usually be the idea. Okay, so it's clear, the setup is clear? So the thing to notice here is that n is very big. So there are about 50,000 of these small blue particles and about 50 of these orange particles. So if in physics you can't do a 1,000-dimensional sampling problem, it's not an interesting method, I would say. So I'm not saying it's not an interesting method for you guys, but for physics it's not useful unless you can really do high dimensions. And we're interested in 10 to the 23 particles. for the kind of statistical physics that we're doing. So they have to generalize to high dimension. So what is the method that we use to generate these configurations? Basically, it's just normal, some sort of normal Metropolis-Hastings MCMC, but we use these tailored proposals in which many particles move at once. So usually in Metropolis-Hastings, you'd move one particle, accept, reject, move another particle, accept, reject. Here, you move all the particles in some concerted way, in such a way that you never have to reject, which is quite clever, but it happens to work in this case. So the catch is you never reject anything, but sometimes you just generate the whole configuration again, but spatially inverted through the origin. So, of course, you don't really get around the rejection problem. You end up with a move which doesn't change anything. But it is a rejection-free method. So I'm not going to talk at all about this method, but there are lots of methods in physics for generating sort of clever MCMC methods to sample from this distribution. And you can find it in this paper. And the important thing is that for this method, if the Markov chain has transition rates from state R to state R prime, which is W, then you have this formula which says that the invariant measure in R times the rate from R to R prime is the invariant measure in R prime times R prime to R, in which case the steady state of the Markov chain has this time reversal symmetry. Right? So if you look at sample paths going forward in time, sample paths going backwards in time, they have equal probability if you fix the endpoint probabilities. Okay? So this is what people usually do in physics. So then, what was the year? So then, a bit less than 10 years ago, Werner Kraut and his people, some of whom are here, managed to solve this problem. And this was an important physical problem. I don't really want to talk about it, but the important thing is that there are 10 to the 6, roughly, particles here in 2 dimensions, and they are doing something quite complicated in terms of their collective behavior. And the received wisdom was, with normal MCMC, you can't do big enough systems to solve this problem. But it turned out that with a Monte Carlo algorithm without detail balance, they were able to solve this problem for which very large systems, very high dimensional settings were necessary. And many people were not understanding why this was working. I think that's, at least intuitively, if you go and talk to people, practitioners in the physics community, and say, why does it work? They say, it seems a bit mysterious. Maybe it doesn't really work until they try it and they discover it does work. But, yes, so this is the puzzle, if you like. Why does this work so well? And can we expect it to work well in general? So that's the claim, is that breaking detail balance, or using irreversible Markov chains in your MCMC, generally speeds up convergence to the steady state and relaxation within the state. So it improves the efficiency of your sampling method in a way to be explained. So that was the sort of hand-wavy motivation. What do we really want to do? We need to understand how to compare models with and without detailed balance. So DB is going to be detailed balance, and that means reversible Markov chain, right? So we need to understand how to compare detailed balance with non-detailed balance in a fair way. We need to understand how to measure how fast these things converge to equilibrium, hopefully in such a way that we can prove something and in such a way that will be useful. And then we want to know how much faster are the algorithms, what are the mechanisms of the acceleration, everything else that you could possibly want to know. So these are the kind of preliminary questions, and these are the kind of real questions. And the question that's in our mind, especially with Johannes, I think, is, in physics, detailed balance is somehow associated with equilibrium, and non-detailed balance is somehow associated with non-equilibrium. So maybe by analyzing non-equilibrium Markov chains, we can understand something about non-equilibrium physics, and not just about sampling, even though sampling is important. But I'm not really going to talk about this today, but I think it's something just to raise as a question. Okay, so how do we compare reversible and non-reversible Markov chains in a fair way? Turns out that's a pretty simple question to answer, or at least an answer is fairly simple. If we have a model with transition rates W, we can define a new model with transition rates Ws using this formula. And then this new model is reversible. It has the same steady state as the original system. It has the same typical values for the transition rates. So it seems like a sort of fair comparator. So that is the claim, is that it's fair to compare the system with rate W with an equivalent reversible system with rates Ws. So you might not like it. If you don't like it, you have to tell me something better. I mean, it seems to be fair. It seems to be what people do. And So the notation is a bit loose here. I guess we have in mind processes where the configurations move by discrete jumps. So it doesn't fit with zigzag exactly, but we could be, we're in continuous time, but we could be in discrete or continuous space. And indeed, we could probably be in discrete time as well. Wouldn't really change anything. You just swap this from a probability of a transition to a rate, right? It's all fairly general. Okay, so that's the answer to the first question, is we're going to compare these two models. Second question is maybe more interesting. How should we compare rates of convergence and efficiency of sampling with these MCMC methods? So you can always use the spectral gap. So if you don't know what the spectral gap is, you make a big matrix with all your rates in it, and you analyze the spectral properties of those rates, and if the gap is big, it means you've got a model which converges fast and should therefore generate independent samples fast. If you didn't know that, it doesn't matter, because I'm not going to talk anymore about the spectral gap. But the spectral gap is always available, and it is true that under quite general conditions, the spectral gap of the non-detail balanced guy is no smaller, isn't it? I swapped these two round. This is the correct statement, right? The non-detail balance converges either faster or just as fast. So there is no strict inequality, but what is true is that it's faster. This should be smaller here, I'm sorry. And this paper in JSTAT-Phys 2016 has quite a nice summary of quite a lot of the things that I'm saying as background, so it's well worth reading that one. And as usual with this spectral gap stuff, the proof is just something about, Dirichlet forms and symmetric eigenvalues and eigenvectors, but there's not much physics in it. It doesn't sort of say, you don't see why it goes fast. You just see that it does. And also, if you want to do spectral analysis for that, 60,000 particle system that I just showed you, I'm not quite sure how I would construct the eigenvalues and the eigenvectors. So what are we going to do instead? We're going to use this large deviation methodology. So let's consider a trajectory over a long time curly t, and let mu t of r be the fraction of time spent in configuration r. So that makes most sense if you're in a discrete setting, if you're in a continuous setting, some kind of density. It'll be all right. Just do whatever you have to do. Then, as the time tends to infinity, convergence to equilibrium, or ergodicity, or mixing, or some such statement, says that this empirical random variable, mu t of r, should converge almost surely to the empirical measure, to the invariant measure of the system, right? That's basically a statement about ergodicity of a Markov chain, and any good sampling MCMC method should obey it. So large deviations is to make this statement stronger. So the idea is we want to replace this statement by something a bit stronger. And the idea is that the probability now that this random variable is roughly rho is given by an exponential factor with the time in front. Remember, this time is getting very large. And then this function I2, which depends on rho. And we have I2 of pi is 0, which means that the probability that mu t is about pi goes to 1 as the time goes to infinity. Right? So this is a stronger statement about this limit, and it characterizes it in terms of this function, which has a 0 and is otherwise positive. Yeah, so these large deviation methodologies, they seem to be quite common in statistical physics at the moment, seem to be quite fashionable, and it's quite a nice way of characterizing how well your method is working, because remember that when you try and compute an average of your test function with respect to your simulation, you basically are computing an average of an integral of this thing against your test function, right? So the value of this random variable speaks directly to the value of the test function that your estimate of the test function that you're going to get out of your simulation. Right? Because this is the amount of time you spend in each configuration. You integrate that against the test function. That's your estimate of the expectation of the test function from MCMC. So this tells you something about how bad your estimates are going to be, or what's the probability of getting a bad estimate. If you want a slightly more precise statement, you can bound the log of the probability on the exponential scale above and below by this. If you want an explanation of this approximately equals, you should read a book on large deviations. You need an open set and a closed set containing rho, and bound it on either side. And standard stuff. So I2 is literally a rate function. The bigger is I2, the less likely it is that you're going to get a mu which is far from pi. Right? So you don't want mu to be far from pi, because that means you've got the bad estimate of your thing you're trying to estimate. And the bigger is I2, the less likely it is that mu is going to be far from pi. So what you want to do is make I as big as possible in order to have a good sampler. So I determines the probability we see goes to pi. So comparing detailed balance and non-detailed balance, we can again show faster convergence without detailed balance. Basically, this one's always bigger than this one in the same sense as before. And that is, again, a not very intuitive proof, which you can find in a paper of Joris, you can find in papers of... so this is for finite state Markov chains. This one is for diffusions, basically. And actually, the Markov chain case is also in here, and other places you can also find it. So I could show you the proof. It fits on half a page, but you just take a Dirichlet form and you put some numbers in and you get a bound, and it's a nice proof. Thank you. But it's not very intuitive about physics. What we want to know is what's going on, really. Is it moderately clear so far? At least a few nods. Okay. So in order to make progress, we have to do something a bit strange, which is go to a simplified class of systems where things will be easier, and then we'll try and go back to the hard case at the end. So let's think about a system of many particles moving around in real space, and we'll zoom out so we don't see particles anymore, but we see some density profile rho. And then this density profile rho will obey some sort of continuity equation, and the current typically has something which comes from diffusion plus something which comes from drift, where d is a diffusion constant, chi is a mobility, E is an external field, which need not be conservative, and chi and d are both allowed to depend on the local value of the density, if you want. So that's the scope of this macroscopic fluctuation theory by Ionel and co-workers, and there are a bunch of models which fall into this category where you zoom out. So the idea is really that rho is now a function which tells you where there are lots of particles and where there are few, but it's still a random function. So here's just the classical example, is you have a discrete one-dimensional set of sites. You have particles which live on the sites. There's at most one particle per site. You hop to the left with rate q, you hop to the right with rate 1, as long as the destination is empty. You do something at the boundaries, which is not written here, but probably they can leave and enter again, or periodic if you prefer. And then you want to take the number of sites to infinity at fixed density, such that you really do see a smooth density profile evolving in time. Okay, that's the idea. And in this case, you can just derive well, I can't derive everything, but Ionel and co-workers can derive everything. And you end up with the current being minus the gradient of the density plus the mobility times the field. The field has to go 0 as a system size goes to infinity, but that's not so important. And then the mobility is rho times 1 minus rho times 1 times. So this is a discrete, say, Markov chain. So for fixed L, we have everything that we had before. The spectral gap is better if you have it reversible, irreversible, and I2 is also better if you have it irreversible. So the reversible system would be diffusion, would be q equals 1, right, with some rate. And then the question is, what happens for large L? So now, before I had this mu upstairs t, which was the fraction of time spent in each site. So now rho upstairs t is going to be the empirical density at some point x in the system. So I look at this point x in the system over the whole long trajectory, how much density is there, time integrated, right? Time integrated and averaged. And also let jt be the time averaged current. So number of right hops minus number of left hops across any particular bond in the system. Then as time goes to infinity, you expect the current to go to the deterministic j of rho, which was given on the previous page, and you expect rho to go to rho bar, which is the steady state density. That's just ergodicity again. And in fact, you can do more than that, and this does require some work, but you can prove it. So if you have a divergence-free current, so probably my one-dimensional example wasn't great, but if you imagine 2 dimensions probably. If you have a divergence-free current and assuming no dynamical phase transitions, then you can get a statement on the probability of these fields, which has this large deviation form, and it's just quadratic. That's what you need to see. So this t is a large parameter. It says that everything that is not typical is suppressed exponentially in time, and then there's just some positive quadratic function here, which tells you how unlikely is the unlikely thing. And this thing is called the level 2.5 rate function in the jargon. And then the analog of I2, which was before the probability to observe a non-typical measure, is now the probability to observe a non-typical density you get just by minimizing this thing over all possible currents. That's what's called contraction in the large deviation business. So it's just a way of computing the probability of seeing a density rho, which is not the typical density. So that was fast, maybe. The key point is that we've gone from what I used to call mu, which was the fraction of time spent in each configuration, to what I'm calling rho, which is the average density at a point. So instead of in the whole state space of the Markov chain, I've projected down onto the density at a point to see how many particles live there. And then I'm just doing the same trick as I did before with the level 2 rate function to work out the probability that this rho is not the typical rho, which would correspond to the ergodic case. Okay, so within this macroscopic fluctuation theory, it's known that we can always decompose the current into a symmetric piece and an antisymmetric piece, where the symmetric piece is what you would get for the equivalent detailed balance model, and JA is the rest. So this is known. So when we make the system irreversible, that corresponds to introducing a finite JA, which corresponds to introducing a finite drift field from before. And we always compare models with fixed JS, because that's the detailed balance part, which was the original thing from the beginning. And then what's important is that these two currents turn out to be orthogonal, in the sense that for any rho, if you make this integral over all space with a mobility sandwich between the asymmetric and the symmetric current, you get 0. So this is not an orthogonality of currents at any point. It's an orthogonality of the field, if you like, in the sense that there's an integral. Yes, that's what that says. And the final thing that we need from MFT is that JS follows the free energy gradient. So you should think of F as being the log probability of the density. Doesn't really matter what it is, but that's what it is. And then this current follows the gradient of the probability. The JS is a pure gradient. In that sense, detailed balance relaxation corresponds to gradient descent in the space of free energy profile. But JA is obviously not a gradient. So now finally, here's the picture which I've been trying to motivate all this time as to why it might be good to break detail balance when designing these samplers. So this is my picture. Each point in this picture represents a function, which is a density profile. So you should imagine this is a two-dimensional cartoon of a very infinite dimensional space somehow. But every point on one of these contours represents a density profile. And then these are contours of the probability of observing that density profile. So somehow contours of the probability in the invariant case, or of the posterior. And this is the equilibrium state here, which should be the global minimum. And it's pretty convex, because we're in this funny space of density profiles. I think they are quite convex in this space. So what I said to you was that if you have just detail balance, then you just follow the gradient. And what that means is that in places where the gradient's very shallow, the relaxation is going to be very slow. But in places where it's steep, it's going to be fast. So for that to make any sense, you need to have, some sense of distance on this funny space, but we'll get to that in a minute. The important point is that the non-detail balance motion is orthogonal to the detail balance motion. So it does not take you at all any faster towards the equilibrium state. But what it does is it takes you around these level sets, and it takes you around these level sets in such a way that you get away from these horrible places where the gradient is very shallow, and you might suddenly find yourself now in a place where the gradient is much steeper, and then you can make progress back towards the minimum. So of course the converse also holds. If you start here, you'll get wiped away back out to here, but it turns out that's less important than the opposite case. So I like to think of it in terms of there being a door. So you wander around until you find the door, and then you fall through the door into the center. So for this to make sense, we need a metric structure on this space. You can do that with these Wasserstein metrics. So this is not at all an original reference for that, but it's a place where you can find it for this setting. So that's what I said already. You can also go away from the steep regions. But on average, we go faster. So that's the cartoon. So can I just back it up with just a few equations? Let me just do that in the last 5 or 8 minutes or something. So this is the probability to observe a non-typical density in current. It's given by this level 2.5 rate function and a factor of the time. And this level 2.5 rate function is just this quadratic formula. Possibly this 4 was missing before, but anyway, it's here now. So it's just a quadratic. So J is the current that you see, and big J is the current that you should see. So little j is the empirical current, and big J is the expected current. So, as you go to long times, basically the probability of seeing deviations between the expected and the typical current is small because you're taking an average over this very long time period. And then the density kind of appears everywhere. It appears in the mobility and it appears in here. The second thing we need is that we can write the current as the symmetric part plus the antisymmetric part. But these two currents are orthogonal, and that the symmetric current is the gradient of something, which turns out to be the free energy. And then we want to show that this I2 of rho, which is our measure of speed of convergence, which is the inf of, this should be rho j, I'm sorry. So we have to inf this thing over currents such that there's no divergence with a j here. That gives us I2 of rho, and we want to show that's bigger in the irreversible case compared to the reversible case. And then that's all we have to do, and then we've proven speed. So here's the formula. Oh, no, so here's the formula for the symmetric case. So I've just set big J to be Js. We just multiply this out. Hopefully I've got it right. And then 1 over chi times Js was a pure gradient. Then you can use integration by parts, push the gradient onto the divergence. The divergence of J is 0, and so this thing vanishes. So I didn't show it, but it's 2 lines to show that this term vanishes by the gradient structure. And then we have to take the inf of this I2.5 over J, but it's easy to take the inf. If this term's not here, it's easy to take the inf. This just goes to 0, and you're left with this. So the I2s, which is the convergence rate for the detailed balance model, is just basically the square of the current in some funny norm. And this all depends on rho, right? Everything is for some fixed rho, but we just suppress it. Okay. So here's the formula for the level 2.5 with the asymmetric current. Multiply out the brackets and hope that I've got it right. So I've kept this one. So then you see that this one is the same as this one here, so that still vanishes by the same argument as this. And this one is going to vanish by the orthogonality formula, which I gave on the previous page, right? So JA and JS are orthogonal. So this one's going to go away. So then you're left with I2.5 is just this level 2 rate function for the symmetric case, plus this thing. This thing's definitely not negative, so that tells us that when I inf this, when I take the minimum of this over J, I'm going to get something which is definitely bigger than this I2s. And so it definitely does indeed go faster. And I was slightly rude earlier about the proofs not being very intuitive. So I feel like this proof is slightly more intuitive because it has this sort of geometrical thing underneath, is that it just has a gradient structure and an orthogonality structure underneath, and that's really all that I used here. And that's why I showed this picture earlier with things sweeping around the contours of the free energy. We can get an exact formula for this speed up, but we need to solve a PDE. So we can get an exact formula for this in terms of the solution to a PDE. Yeah. So I didn't show that, but it's in the paper if anyone wants to see it. So I'm coming at this story in a rather strange way, because I started with a very general statement about Markov chains and diffusions, and it always going faster when you break detail balance. And then I went to this funny setting where you zoom out, you can't see the particles anymore, you do everything on density profiles. And so now I want to come back to the question that I started with, which was, if I'm not on the hydrodynamic scale, does any of this story that I've just told you have any useful meaning? And the answer is yes, it does, So do these geometrical results have any counterparts for general Markov chains? So the answer is yes, but it's a bit less clear what's going on. So within the MFT, this is just saying what I've already said. Within the macroscopic fluctuation theory, we have this quadratic rate function, which looks like this. And it just looks like some sort of squared norm, right? And then we have this orthogonality, which looks like some kind of inner product being 0. So for a general Markov chain, there's an explicit formula for this, something a bit like this level 2.5 rate function, but it's not at all a quadratic. And that makes life more complicated. So I'm not going to show any results, partly because it's still being written. But I'll tell you the answer, which is that the fact that I can draw this picture with these contours and these gradients is only possible because there's some geometrical structure behind here, which is no longer there in the general Markov chains. But the algebraic structure is still there exactly the same. So there's still a formula which looks like an orthogonality, even though there's no metric structure. And there's still something which looks like a squared norm, even though it doesn't have enough properties to be a norm, like it doesn't have triangular inequality, for example. So what happens when you go to general Markov chains is that the structure survives, but the geometrical interpretation is kind of lost. And the geometrical interpretation appears only when you zoom out far enough to see this, this representation in terms of density, for example. Okay, so this would be what I think is where we are. So I think there's quite good evidence that these irreversible samplers are quite good. There are proofs that they should be good. There's empirical evidence that they are good. I guess the contribution of this picture is to try and say something about why they are good and therefore what circumstances one might expect them to be useful. And this is my picture for that. I think this large deviation rate function idea popularized by Spiliopoulos is quite a nice one for characterizing this sampling efficiency. And we can compute it using geometrical properties of the model. We don't know if this is more useful more generally. I don't want to really say anything about it. Let me just say one very quick thing. This is just a model system we did for non-interacting particles or some zero-range process. It's got two minima in the posterior, and the rate of convergence is therefore dominated by the time to cross this barrier here between these minima. So the only reason I bring this up is that this picture doesn't really help you get over minima, get over maxima of the minima of the posterior or maxima of the minus log likelihood, right? So this is really a way of getting away from shallow regions, but it doesn't take you over big barriers. So that might be a hint for why this can tell you something about when it's a good method and when it's not a good method. But that's all I want to say. That's all I've got time for. Thanks for listening, and I'm hoping to have discussions with you for the rest of today to understand more what goes on in the stats world. Thanks a lot.
Time for a few questions.
I'd like to ask something about the I 2.5 because so I know this I kind of know this other large deviations paper, and I think if I remember correctly, the I that they use it only depends on rho, and yours depends on rho and J. Is this the difference?
So that's right. So yeah, maybe it was too fast. So sorry, on the slide a minute. So here's what you need, right? So this is what you really want. This I2 of rho, which only depends on rho. So this is the thing that you want to make a bound on, because it tells you the probability of seeing something which is not the right thing. The thing which we have an explicit formula for is this level 2.5 guy, and it has a nice simple quadratic. And then you have to take an inf, you have to take a minimum to get what you want. So all the work goes into either bounding or estimating this inf, right? So you have to get down from the space of currents and densities down onto the space of densities in order to prove what you want. And this you have to do some work at some point to do that.
And just, this name level 2.5, I mean, I've heard like level 3 and so on, but like how does it relate? Or
so level 2, so it all goes back to Donska and Varadhan in the 70s, I believe. So level 2 already had a name, and level 3 is something very detailed to do with very detailed properties of the fluctuations of the sample paths, which I don't fully understand. And there is also level 1. And then Bertini, Gabriele, Fagionato, a few years ago, they discovered this explicit formula that's intermediate between level 2 and level 2. Between level 2 and level 3. So they called it level 2.5. And now there is an industry, there is level 2.49 and level 2.1999, and all these fun things. But
so thanks for a great talk. With detailed balance, there's a clear protocol about how you can devise a sampler that converges to the equilibrium distribution. Is there anything like this for non-equilibrium samplers to show that they will converge to the correct stationary distribution, or to design them so that they do?
yeah, so it's work, isn't it? So you can do event chain style lifting type things. It's not quite clear to me how that fits into this language because we don't expand the state space at the point where we break detailed balance. But we could expand the state space first and have a reversible one on the big space and then break detailed balance in the second step. So I think we're going to hear about such methods in the rest of today. What we did was just do it explicitly, and that's kind of a pain, but sometimes you can do it.
One more question, yeah, Andrew.
So in that picture you had in that picture you had where you were kind of exploring the level set with the non-reversible, yeah, that one. So in this kind of two-dimensional system, you can kind of see that you're always kind of going to go in the right way. But imagine your level sets are really, really, really high dimensional, and then there might be only very few directions which are beneficial. So my question is, do the rate functions kind of have any dimensional dependence in the general model?
Yeah, that's a very good question, isn't it? I mean, the problem with this business is that everything is a bound, and it's not even a strict bound. It's always a bigger than or equals to, right? So all you really know is that you don't do any worse by doing all this hard work to make your system irreversible, and then you have to test case by case. So maybe you can just see something here. So maybe if you think about maybe one can try and think about the dimensional dependence of this. That's as far as I can go right now. I mean, maybe there's some argument, but I don't have one.
Okay, I think we should wrap it up for now. So we've got coffee outside now, and I think we're back in half an hour. So if we can thank the speakers again from the first session.